Okay, lecture 12, applications of differentiation. Differentiation is so useful so that you can apply to many different things in robotics. The first one is extremum here. So let's look at this thing here. Okay, so the fact, differentiation is not just speed. Of course, differentiation was so important and useful because we can compute the speed. But of course, there are a lot more. What's more? Okay. Derivative is equal to 0 means the rate of change is equal to 0, right? So therefore, not changing. So therefore, not increasing nor decreasing that static point. Static point? Like if you have a graph of a function here, static points are those points where this is not decreasing, not increasing. Those points. And if you take a look at those points, of course, those are maximum or minimum points. So, derivative is equal to 0 can be interpolated as the position of minimum or maximum. Okay? And so we can use that derivative is equal to 0 to find both of them. And we use the word extremum for representing both maximum and minimum. So derivative is equal to 0 is for extremum. Okay. Let's try with this example here. So f of x, we differentiate that, and this is what you got, 12 minus 96, 228, and 144. And of course, you can factor 12 out and get this one here. But that's this. In those examples, as every student know that I started from here and computed the other way around. All right. So this is what we got. So therefore, by setting this one is equal to 0, we got x is equal to 1, 3, and 4. Okay? And that's here and there and there, here, those 2 points, minima at x equal to 1 and 4. So, setting derivative is equal to 0, we can find maximum minimum. Okay, that's fine. But the one thing I would like to how should I say it? emphasize is that those maximum minimums I was talking about, but they are only in the neighborhood, somewhere close to it, right? And if you look at this one here, say for example, this is maximum, but it says it's maximum. But of course, the function value goes above that value as you move away from that maximum point. So those maximums and minimums are only in the neighborhood. Therefore, we give the name of local max and minimum. Local is an easy word compared to neighborhood. Neighborhood, forget about that. Local, all right? Then, the next thing is that suppose you are given unit interval or region in which what is the maximum, what is minimum. Okay? Then now you're talking about the maximum and the minimum within this region here. Say, for that, differentiated this one here and of course endpoints here. So I compute the values of the functions at endpoints and derivatives here and compare them. Like those 1, 2, 3, 4 points. If 4 happens to be the end point, so although it is an extreme point and it is also an end point. That happens quite often. So what's the maximum? 43. And what's minimum? Negative 16. Therefore, what we got is those two. Maximum, the maximum at x is equal to 0, the value 43, the minimum at x is equal to 1, and the value is negative 16. Okay? So, strategy is to find the extrema and check the endpoints and compare them. That's the way you can find the us. Now, you may be wondering why maximum and minimums. And of course, in high school, you have done this computation many times probably. But for us robotics engineers, they always have hard limits for ranges of motions for joints. That's the reason why we want to compute the maximum minimum. Like this one here, this joint here, it can move to this but cannot move any more to this side. The other side, this is the maximum it can go. It cannot go the other way around, right? So, well, there are some people who can go a little bit more than that, but my joint doesn't go any more than that. So there is always a hard limit. And what's going to happen is that suppose a joint motion range be theta A and theta B has to be within this range, and joint angular trajectory is given by theta, or I should write this one T here. Theta of T is equal to FTPQ within T0, TF range, okay, where P and Q are parameters which you can adjust, okay, parameters you can adjust. As the robot kick, we had P and Qs, capital P and Qs, remember? Okay, so the question is, find P and Q that makes this trajectory realizable. Realizable meaning that in equation form, it says this. Theta A, theta B here, F, this trajectory, entire trajectory stays within this bound for all T. By the way, this one here is for all. For all T within this interval, okay? So, answer is of course, find the maximum, minimum, and make max and minimum within this range. Then everything else should be within that range, right? So therefore, instead of checking every part, the only thing you have to do is to find the maximum, the minimum, and adjust P and Q's so that they are within this range. That's handy. So for that, check extremas and endpoints. That's it. That's all you need to do. Okay. So then the next question probably is that df dx is equal to 0, derivative is equal to 0 will give you an extrema, or extrema is a plural. So an extremum or extrema. But anyway, is that a maximum or minimum? Is there any way we can check that? And for that, we can use this fact that derivative is greater than 0, it's increasing, right? Derivative is greater than 0. Rate of change is positive, so therefore it must be increasing. The other way around is also true. Less than 0, decreasing. So let's consider two cases. Case A, case B. Case A, derivative is equal to 0 at this point here, but before that, it was positive, and after that, it's negative. Case B, the other way around. Derivative is equal to 0 at this point, and negative before and positive after. So, well, let's take a look at this one here. Here, this is positive, and here, this is positive. So therefore, those before 0, that's function is increasing, and after this derivative is equal to 0, function is increasing, naturally. And if you take a look at the other side, this is less than 0, therefore what's going to happen is that this is decreasing and this is decreasing. So, if that is the case, this is increasing, get to 0, and decreasing. So this is obviously a maximum, and this one here is decreasing and increasing, so therefore this must be minimum. Okay? So that's easy to find. Easy? No, because you have to draw this curve. You have to find out if that is positive, negative, positive, negative. Okay? But can we do a better job? Okay, so, well, let's take a look at the derivative a little bit more closely here. But here was positive, 0, negative. So therefore, df dx, derivative is decreasing. This one here is the other way around. Derivative is increasing. So the rate of change of the derivative is negative, right? This is decreasing. And this one here is increasing. So the rate of the change of the derivative is positive. So therefore, this is the rate of change less than 0 and rate of change is greater than 0. And what is this? Those are second derivatives, right? So therefore, the sign of the second derivative can be used to find whether it's a maximum or minimum. There is a possibility, right? And of course that you don't believe that, do you? So let's use this example once again and to find out, see if that is the case. Now derivative is this, and second derivative is that, and the extrema at x equals 1, 3, and 4, we already know that. So let's compute the second derivative at x equals 1, which is greater than 0, and 3, that's negative 24, that's less than 0, and at 4, that's 36 greater than 0. Therefore, the first one is greater than 0, so that must be minimum. This is less than 24, that's maximum. This is greater than 0, that's minimum. And that's exactly what we have, right? So therefore, second derivative test works. That's great. So the strategy is to find the extrema by setting df dx derivative is equal to 0. And compute the second derivative and evaluate that second derivative at those extremum points and see if that is positive or negative to find out minimum or maximum. All right? So this solves everything? Well, not quite. Let's look at this. Coffee break. What happens if the second derivative is equal to 0? Second derivative greater than 0, that's minimum. Less than 0, that's maximum. But what happens if that is equal to 0? Well, let me repeat myself. First derivative is equal to 0 is extremum, and at the same time, second derivative greater than 0, minimum, less than 0, maximum. So therefore, it's equal to 0 is which? Question mark. All right? And to consider these kind of cases, it is much easier, it is constructive to consider solid example. X cube and X force. We all know how this X cube looks like and X force looks like. Okay? So setting the first derivative is equal to 0 and X is equal to 0 is what you got. So therefore, X equals 0 is an extremum for both of them. Right? That's perfectly fine. But both second derivatives are also 0 because first derivative 3x, second derivative 3x squared, so second derivative is 6x. Here, first derivative is 4x cubed, so therefore the second derivative is 4 times 3, that's 12 times x squared. Once again, 0. So both of them are equal to 0. But at the same time, we know that x equals 0 is an inflection point for x, if x is equal to x cubed. Wait a minute, inflection point? Never seen before, right? So let me just draw a diagram here. This one here, inflection point. Well, x cubed look like this one here, right? So it increases and becomes static. In other words, derivative is equal to 0. And after that, it decreases if that is a maximum. But no, it keeps increasing. So this is called the inflection point, inflection. The important part is that here, this is convex, this is concave. Well, this is, how should I say? The curvature is different, but anyway, it becomes 0 and goes up. That's the inflection point. And x equals 0 is a minimum for gx equals x force. Okay. So what is the conclusion? Conclusion is inconclusive. Ha! Inconclusive. When the second derivative is equal to 0, anything can happen. Inflection point or minimum or maximum. If you look at, instead of x to the fourth power, negative x to the fourth power, that's the other way around. That's the maximum. So for that is equal to 0, you just need to look at the function in the vicinity, meaning locally. You have to plot a diagram like this one here. Too bad, but that's what you have to do. All right, that is done. So the next thing is local versus global. Now, we discussed in the two examples, first one, local minimum, local maximum, and then I limit the range of x value. Or I should say I will use another different word for it. And then you have only one max and one minimum, the maximum and the minimum. Okay? So let me talk about that. If that is a maximum or minimum only in the neighborhood, this neighborhood, fancy word once again, those are called the local extremum. I already said that. So there could be more than one local extremum. We have seen that already. And overall, meaning that entire range of x or whatever, or 0 to 4, that was the range we had. That is called a global extremum. One each of global maximum and global minimum. So unique ones. Global in where? Concept of domain. That's very important. Okay? And the domain of a function y is equal to fx is the entire area x where x can be. So x can vary within this range here. This entire thing is called x. So that's domain, where it started. The function f takes the value f into this one here, y. So the range of a function y is equal to fx is the entire area y where y can be, the value y can be. And for that, we use this notation here. F starts from x, goes to y. So for that case, within this y entire region, you can have one global maximum and global minimum. Okay? All right. That's simple enough, I guess. So you can find local maximum and minimums if you have one variable. But remember, robots has many joints, right? So you will deal with functions with multi-variables, many variables. Okay? So, for example, let's take a look at, well, we can draw a graph in 3D. So let's take a look at the function of two variables. Simplest one, two variables, z is equal to fx, y. Like this one here, this is plotted by using a software called a MATLAB. Okay, our function looks like this one. Y direction and the x direction, and that's z direction here. Okay. So, second fish under willow tree. To find the minimum or maximum, namely extremum, what we do. First, the single variable case, we set the derivative is equal to 0. Well, second fish under willow tree. Well, the same technique can be used, maybe useful for this case as well. So set the derivative is equal to 0. And of course, since you have two variables, so which one? Which one to set 0? And naturally, the answer is both. And set both of them. Okay, so we get the z delta x, y delta. Well, there are two variables, and this one here is differentiating in terms of x, so therefore it has to be partial differentiation. And delta z, delta y, and both of them set both of them equal to 0. And I use this notation of star here, denotes the position of extremum. Well, so in the diagram, this here, well, somewhere on here. Okay. Okay, so that's what we want to use. Okay. Well, so extremums, you only set the set of equations, those two variables and two equations. So you may be able to solve. But are they minimum or maximum? In that diagram, it was a minimum, okay? But what can we do? The third fish on the willow tree, one more time. We can use whatever the technique we have used for the single variable, we may be able to use it here as well. So the second derivative. But second derivatives are a lot more complicated, aren't they? Differentiating which derivative? There are two derivatives with respect to which variable. There are two variables. So that their combination, there are 4 of them. Which one are we going to use? The answer is every one of them. And put together into a matrix H. H comes from this name here. This one is called the Hessian matrix here. So put together those partial derivatives into the second derivatives into a matrix form. And using this one here, I am not going to prove this, but the following criterion can be used. If determinant of H is greater than 0 and this one here, x squared, the first element, is greater than 0, that's minimum. And if the determinant is greater than 0 and the first entry is less than 0, then that's going to be maximum. That's easy. Aha, there's one more line here. Okay. If determinant H is equal to 0, this is called a saddle point. Once again, a new word here, saddle point. Okay. What is this? That's this. Saddle point is increases along one direction and decreases along another direction. So, like this one here. It increases along this direction, but decreases along this direction. Right? So that point here, this point is a saddle point. That can happen because this is the two derivative, the three-dimensional space. Okay. Okay. Another case. Remember that second derivative is equal to 0, anything can happen for the single variable case. And same thing is true here. Determinant S is equal to 0. What we can have? Pretty much the same as this one here. Can't tell. In mathematics course, this doesn't happen too often, right? Can't tell. We don't know what's going to happen. Okay? It depends on higher derivatives. I am going to talk about that in the next application of differentiation. Okay, and I will show you why this is the case in the next lecture. Okay, example. Well, this one here, z is equal to fxy, 3x squared y squared plus 6xy plus 10x minus 6y plus 5. Well, this looks like squared, plus, plus, plus. So it seems to be going up to the infinity anyway. So setting the derivative is equal to 0, we get those two equations here. That. And you can, of course, solve that. 4, 6, 2, 6, xy is equal to this one here. So therefore, inverse is equal to 2, 3. 2 and minus 3. So the extremum is at 2 minus 3. Is at a minimum or maximum or saddle point? Okay, let's look at this determinant h. Okay, since this is dz dx, if you differentiate this one here one more time with respect to x, that's 4. And y, this 6. And this one with respect to y, x, that's 6. In terms of y, you have 2. So the Hessian matrix is nothing but the coefficients of those. And the determinant of this one here, of course, that's 8 minus 36 is minus 28, less than 0. Less than 0. So, what is this? This is a saddle point, like this one here. Actually, this graph is the graph of this function. Okay? So, this is a saddle point, isn't it surprising? Well, my first intuition is that since this is plus, this is plus, this is plus, so at least at 6 squared, y squared goes to infinity very fast, so it should go to infinity regardless. So I thought it was a minimum, but not really. This 6 times xy, when x times y is negative, goes to infinity faster than this one here, 2 or 1. That's why this one goes down to negative infinity in one direction. Okay. All right. So that is the end of this lecture, and next time I'll talk about the second application of the derivative. Thank you.